Let's work on a few more problems that are in a comprehensive calculus 1 class. So this would be Calc 1 review. I guess this would be part 4. All right, so we've got air being pumped into a spherical balloon. Now a sphere has a volume of 4/3 pi r cubed. If you've got a printed copy of this thing, I've got 1/3 pi r cubed. That is wrong, okay? So at a rate of, at a rate of 3 cubic meters per second. This makes this a relative rates problem, or related rates problem. So the question says, at what rate is the radius of the balloon changing when the radius is 6 meters? So r equals 6. So the question is, what is dr dt, the rate changing of the radius, so dr dt at r equals 6. So that's the question. So related rates. Well, we need to take the volume. So dv, and we're trying to do this with respect to time. So dv dt is equal to, well, what's the derivative of this? 3 times 4/3 pi r to the second. So that's going to end up being 4 pi r squared. But r is not the variable we're working on. So we've got to go dr dt. Well, that sets us up beautifully because we've got all these things here. So we know that dv dt, this is dv dt, and in case you're wondering why I know that, partly because it was read that way, but also that's a volume, okay? So 3 meters cubed per second is equal to 4 pi, well, what's r at this moment when they ask us? 6. So 6 squared times dr dt. Okay, well, 6 meters squared, okay? So that's actually meters squared, so 4 times 36, which is 144, and pi. So I'm going to divide by 144 pi, and that's actually meters squared. This is meters squared. So I'm going to take this 144 pi meters squared. So meters cubed over meters squared, we're going to have meters. 144 divided by 3, okay, that's 48. So we've got 1 over 48, there's a pi there, and then this is meters per second is equal to dr dt. So that's a related rates problem. All right, next I've got a few kind of arbitrary integrals. So here's an integral. Let's take 1 over x cubed plus 1 over the square root of x minus 5 sine x dx. Okay, you can't do integrals of fractions generally, so we've got to make this into a power rule. So this is going to be x to the minus 3 plus x to the minus 1/2 minus 5 sine x, and then dx. So lower the power, x to the minus 2 over minus 2. This one, or raise the power, excuse me, you raise it up 1. Okay, this one is x to the minus 1/2 plus 1, which is x to the plus 1/2, over 1/2, so that's like times 2, times reciprocal, and then minus 5 sine x. Well, the derivative of cosine is minus sine, so this is going to be plus 5 cosine x, and then plus c. So kind of an arbitrary integral, just with some pieces. Let's look at another one. Here I've got one that is 2t to the 4th minus t plus 2 over t cubed. Now that almost looks like it should be substitution, but it's not, because this is not really located a lot up here. So I need to just take each piece and divide it. So I get 2t to the 4th over t to the 3rd. That's going to give me 2t. Minus t over t to the 3rd, that's 1 over t squared, so minus t to the minus 2. And then 2 over t squared, or t cubed, is 2t to the minus 3 dt. Get that there? So integrate 2t's integral, 2t squared over 2, that's t squared. And then minus t to the minus 1 over minus 1. Okay, so those cancel. And then you've got plus 2t to the minus 2, raise that up 1, over minus 2, and then plus c. So it ends up being t squared. This is 1 over t, it's plus 1 over t. The 2's cancel, we've got minus 1 over t squared, and then plus c. So you basically do long division, although it's a little easier than long division. Here's another one. This one has the integral of the square root of x plus 2 all squared dx. Now I cannot really do substitution, so I'm going to expand this out. Square root of x plus 2 times square root of x plus 2. This times this is x. This times this is 2 square roots of x. Here's another 2 square roots of x, so we've got plus 4 square roots of x. 2 times 2 is 4. So our integral is actually of x plus 4x to the 1/2, that's this, plus 4, and then dx. So the integral of x squared over 2, plus 4, and then raise this power up 1, x to the 3/2, then times 2/3, and then plus 4x, and plus c. So we can have 8/3 here, that's a times. So x squared over 2 plus 8/3, x to the 3/2, plus 4x, plus c. All right, so just some kind of arbitrary problems that we're working on. Let's go with another one. This one is an integral of sine to the 4th of x times the cosine of x dx. Now this one is a substitution. It's got sine and cosine. I'm going to choose sine as my substitution because it's raised to a power. So u equals sine x. So the derivative du is cosine x dx. I skipped a step there, but here is du, and here's u to the 4th. So what's our result? Well, it's going to be u to the 5th over 5 plus c. What's u? U is sine. So sine of x, sine to the 5th of x over 5 plus c. So that one turned out pretty quick and easy. Now let's go again and see what we come up with for something else. Change gears again. Let's do a summation problem. This one has k equals 1 to 36 of k squared minus 5. Now you might remember some formulas for squares and such. Let me just pop that out there. So if I go from 1 to 36, the formula for k squared is k, or actually it's n, excuse me, because this is n. So let me do this. Okay, so k squared, let me set that up. K equals 1 to n, should be this. It should be n plus 1, times 2n plus 1, all over 6. Now you may or may not memorize that one, I don't know. Constants, k equals 1 to n of a constant is equal to the constant times n. So what do we have? Well, just plug these in. K squared becomes n is 36. So 36 times 36 plus 1, that's 37, times 2 times 36, which is 72, plus 1 is 73, and this is all over 6. That I promise that'll never be a fraction when you cancel it out. And then we've got to subtract 5 times 36. Okay, so here's 6. And getting the calculator out, we can go ahead and calculate the value of this. So what do we have? Well, we've got 6 times 37 times 73. Okay, so 16,206, and then minus 5 times 36, which is minus 180. So minus 5 times 36. And there we go. So we had 16,206 minus 180 is equal to 16,026. All right. So just a little bit of summation work. Now, one more type of a question that's pretty common in a calculus class. Let's say we have f of x equals 1 over x. The interval that we're talking about is from 1 to 9, and we need to use the area using 4 circumscribed rectangles. Okay, so that's what's asked for in this particular question. It's not the actual area, it's an estimate. So I've got to take this, first of all, and divide it into 4. So 9 minus 1 is equal to 8 units, divided by 4 gives me 2, so that's the width. Okay, 1 over x is a decreasing function. You might remember it looks like that. Okay, so I'm going to have circumscribed coming from the left. So my endpoints are going to start at the left. So 1, and then 3, and then 5. I'm counting by 2s, and then 7. Okay? Now, that's the x value of each. Okay? Now, what's the y value of each, or the f of x value? 1 over 1, 1 over 3, 1 over 5, 1 over 7. Okay? How wide is each one? Width is 2. So what's the area of the rectangle that's indicated here? 1 times 2 is 2. So area, 2 times 1/3, 2/3. 2 times 1/5, 2/5. 2 times 1/7, 2/7. So the total is 2 plus 2/3 plus 2/5 plus 2/7. And that's a pretty big fraction, not too big a deal, I suppose, but let's try it on the calculator. We've got 2 plus 2/3 plus 2/5 plus 2/7. Answer right there. I like fractions, I like exact values, so let's do that. We get 352 over 105. So 352, 105. Now that's a little bit more than the actual area, but it's a way to estimate. So, okay, let's see here. Let's try to find something else to look at. Let's talk about Rolle's theorem. Rolle's theorem has to do with the slope and of a tangent line versus the slope of a secant line. So the problem I've got is f of 4 is equal to 5, and f of 18 is equal to 5, and f of x is continuous and differentiable on an interval from 4 to 18. Those are the x values here. So what can you say is going to happen to the function somewhere in there? Well, Rolle's theorem says that we look at this, these are the same level. So, you know, here's one point and here's another point. They're both 5 units high. So they're horizontal, so the slope here is 0. If this is continuous and differentiable all the way between these two, then what we can do is we can say that f prime of c, some value c that's in here, so c is in there, I put c is in there, is also equal to the same slope, at least one place. Okay, so kind of an interesting fact. Rolle's and mean value theorem are similar, but Rolle's has got to be a horizontal line. Now let's talk about graphing. Just some quick work on graphing. Let's take a function. F of x is equal to 4x over x squared plus 1. I'm going to give you the derivative. F prime is minus 4x squared plus 4 over x squared plus 1 squared. And f double prime is 8x times x squared minus 3 all over x squared plus 1 cubed. All right, so I think those are accurate and they're simplified. Now, first of all, what are the x-intercepts? Well, they come from here. So that would be where 4x equals 0. That's the only option. It's the numerator of the original function. So x equals 0. Second question, vertical asymptotes. Those actually only come from the first function, the original function anyway, and that is where x squared plus 1 equals 0. No solution, because that would be plus or minus I, and we don't use I in Calc 1. The next question would be critical values. Critical values are from the first derivative, so f prime of x, and so that would be either 0 or undefined. Take a look at this. It's never undefined, so let's just make it 0. And 0 is actually just addressing the numerator. So take this, set it equal to 0. One way you can deal with this is you can just move the negative over and say 4 equals 4x squared. So 1 equals x squared. Now you've got to be careful with algebra, because you take the square root, you better take plus or minus. So you get two values. So critical values are plus or minus 4. Now, what else? Let's talk about the inflection values. Okay, so inflection values. Inflection. Let's see. Inflection are from the second derivative only, where it's either 0 or undefined. So f double prime is either equal to 0 or undefined. Again, this is not going to be 0, so it won't be undefined because its denominator 0 is undefined. Take these. So 8x times x squared minus 3 equals 0. That gives us x equals 0 for this one. And it gives us x squared minus 3 equals 0 for this part. Well, this is x squared equals 3. X equals plus or minus the square root of 3. Now, an estimate from a calculator is not that good, so leave it that way. I don't have the y values. If you want points, you've got to go to the original function. Last question, I guess, here is what happens at x equals 5? Is it increasing or decreasing when x equals 5? Well, increasing and decreasing relate to the derivative, the first derivative. So put 5 in the first derivative. Minus 4 times 5 squared. So that's minus 4 times 25 minus 100 plus 4 is minus 96. This is 5 squared. 25 plus 1 is 26. 26 squared. Now you don't even have to figure that out. If you notice, it's always positive. So that is negative. Okay, it equals a negative, which implies decreasing. So it's decreasing there. Okay. All right. Oh, I got one more question, and then I'll stop here. What about at x equals 5? Is it concave up or concave down? Now, again, this is positive all the time. Square plus 1. Positive, cubed, positive. So I'm going to just stick the numbers in here. So 5. 8 times 5 is 40. That's positive. 5 squared, 25 minus 3. That's 22. So it's positive, which implies that it is concave up at 5. At x equals 5. So it's decreasing and concave up. Graph looks like that. Okay.